Alright, good morning class. Today we're going to continue with the stuff that we didn't finish from lecture 3.3, which is this practice problem and then another practice problem. And then we'll get started with lecture 3.4 and hopefully finish this unit today. If not, we'll continue a little bit next class. So last class we started with this problem and we stopped at D. So the last part here is to find the isotropic pressure and isotropic composition for the temperature of 318.15 Kelvin. So in this case, we have a mixture of methanol and methyl acetate. So as we said before, methanol is the more volatile. We have the equations for the activity coefficient, and we have A, which is part of the activity coefficient equation, and we have these two equations which basically follow Antoine's equation defined Psat. Alright, so we go down and we're going to check. The first thing we're going to do is check if an isotrope does actually exist. So I'm showing you extra steps here. We already know an isotrope does exist, but the step here will kind of reconfirm that. And what we're going to be doing is using the relative volatility. Alright, so in this case, we're going to do a check using the relative volatilities. We're going to write relative volatility, check if isotrope exists. In this case, the equation was alpha 12 equals y1 over x1 over y2 divided by x2. And then from the modified Raoult's law, we said that this is the activity coefficient 1 multiplied by P1 sat divided by gamma 2 P2 sat. And if we plug in the equation for the activity coefficients, we put the exponential, then we have a x2 squared P1 sat over exponential a x1 squared P2 sat. Now we're going to look at this equation and look at the limits when x1 approaches 0 and x1 approaches 1, meaning when I have 0% methanol and when I have 100% methanol. So just to remind you guys, at the isotrope, what do we have? y1 equals x1, right? Same thing, y2 equals x2. And the relative volatility would be what? This here. 1. So we're doing the limit checks to see, do we cross 1 anywhere in the limit? Okay, so we're going to check alpha 12 when x1 close to 0, and then alpha 12 when it close to 1, x1 close to 1. If it crosses 1, like if 1 is 0.5 and 1 is 3, then we know it crossed 1 somewhere. That means an isotrope exists. Alright, so let's look at that. So we got alpha 12 as x1 approaches 0. So looking at this equation, exponential ax1 squared. If x1 is 0, what happens there? Exponential to the 0, which is? This here would be 1. Right? Exponential to the power of 0, so we just get P2 sat, like we said. So we write P2 sat and exponential of A only. Why? Because x2 would be 1. If x1 is 0, x2 is 1. So then we just put A, and then we write P1 sat. Saturation pressures are functions of what? Temperature. We have the temperature. We can plug in the values to the equations that we have, and A is also a function of temperature. Plug in that value in there, do the math, and we get a value here of 2.052. Then we apply this to x1 approaching 1, and we find, again, simplifying the equation, P1 sat over exponential a P2 sat. Same thing, we have the temperature, plug in the values, do the math, you get a value of 0.224. So that means somewhere between x1 equals 0 and x1 equals 1, I have relative volatility of 1. Right? Between 0 and 2, somewhere in between, I've crossed the value 1. Meaning that an isotrope should exist. So therefore, add some composition between 0 and 1, alpha 1, 2 equals 1, which is at the isotrope. And graphically, to think about this, if I plotted on this graph alpha 1, 2 on the y-axis, and on the x-axis we have x1, where we have 0 to 1. When I have an isotrope, alpha 1, 2 should be equal to 1, right? So let's draw that as a black line, and this is my reference point. Okay? If I check the limits of alpha 1, 2 at 0 and alpha 1, 2 at 1, and I find they don't cross the 1 line, that means they probably look something like this. Let's say they look something like that. Okay? This means they never cross the 1, meaning there is no isotrope that exists. So this means no isotrope. But in the case that we had here, at 0 it was 2, and at 1 it was 0.2. So let's say, it was somewhere here, and then maybe somewhere here. If I draw a straight line, as we see here, somewhere along that line, I cross the 1. At that 1, we have what? At this composition, we would have the isotrope. Okay, so this would be here. Isotrope composition. Another scenario could be, where you have, at 0 somewhere down here, and then maybe at 1, x1 equals 1, it's up there, and you would draw some line like that, and you would get the following. So these are two different possible trends that you can find. Two possible trends. All right, so now we've checked if we have an isotrope or not. We know we have one. So now we're going to do the math to actually find it. All right, so now we're going to do finding the isotrope. We know already that alpha 1, 2 at the isotrope is 1, right? So with respect to the alpha 1, 2 equation that we wrote up here, this left side is 1. That means the ratios of the activity coefficients are equal to the ratios of what? The pressures, right? So we can write that down in here. So we got, because of that, gamma 1 over gamma 2 is equal to 2p2 sat over p1 sat. p2 sat, p1 sat are known. So we plug those in, 66.65 kilopascals and 44.51 kilopascals, because we know the temperature. We get a value of 1.4747. So now our goal is to solve for the composition. How are we going to do that? In this case, we have these two equations, and they're both functions of the composition. And we have the ratio of gamma 1 to gamma 2. So we can plug it in there, solve for x. But what we're going to do is we're going to take both the equations, subtract them from each other to get the ratio. Because one of them alone doesn't give you the ratio. But if I do ln gamma 1 minus ln gamma 2 is equivalent to ln gamma 1 divided by gamma 2. All right, let me see here. So we got, starting off with natural log gamma 1 equals ax2 squared. We're going to take the two, subtract them from each other, so we're going to get natural log gamma 1 minus natural log gamma 2 equals to ax2 squared minus ax1 squared. So the left side is equivalent to gamma 1 over gamma 2, natural log. And then here, what we're going to do is we're going to multiply this out. So we're going to have a x2 minus x1 times x2 plus x1 by factoring out the a and then doing math. That's the equation. The right side here is equal to 1 because we have two components. We add the 2, we get that. And then here, this is equivalent to 1 minus x1. So then we can write natural log. In here, I'm just going to plug in the number 1.4747 because we know that from here. And then that's going to equal to a multiplied by 1 minus 2x1. A is a function of what? Temperature, right? So T is given. We can solve for A. The only unknown is x1. So, what's that? 1 minus 2x1. This is 1 minus x1 minus x1. Okay? So then it's 2x1. Do the math, you get that the isotrope, x1 isotrope, is equal to 0.325, which is equal to y1 isotrope, because x1, y1 are equal at the isotrope. With respect to the pressure, so we found the composition here. If you know x1 and y1, you know x2 and y2, right? Now we need to find the pressure, so this is when we're going to use the modified Raoult's law. So for pressure, we have y1 isotrope times p equals to x1 isotrope, gamma 1 isotrope, p1 sat. This and this are what? Equal. So then they cancel each other out. So then the pressure is equal to gamma 1 isotrope p1 sat, which is equal to, do the math, again, gamma 1 is a function of temperature and the composition. So we have the composition, x2. We plug it in, and you're going to get 1.657 times p1 sat, which is 44.51 kilopascals. So you get 73.76 kilopascals to be the pressure at the isotrope where the temperature is 318.15 Kelvin. P1 sat is Antoine's equation, function of temperature. All right, any questions? So we solved for the pressure at the isotrope and the composition in this problem. So now we have another problem where again we have two components, cyclohexane and phenol. In this case, we know the composition in the liquid phase, so x1 is 0.6, and we know the temperature, 417.15, and it's asking you to determine equilibrium pressure, P, and vapor pressure, composition, Y1. So we want to find what's the pressure and the vapor composition, Y1. So we're starting with a liquid, and we're going towards a vapor. We're given that the activity coefficients follow these equations, but we're not given A. In this problem, we're not given A. But we're given other information. The other information is that the system has an isotrope at 417.15 Kelvin, where this is the composition. And we're given that at the same temperature, P1 sat is this, P2 sat is this. So we're given some data points that will help us maybe solve for A if we need it. All right, so now we're going to write down the equation for pressure. Because we're starting with a liquid composition, do we use dew pressure or bubble pressure? What do you remember? Bubble, right? Because we have the liquid composition, we're forming a vapor, the initial bubble. So in that case, the pressure is going to equal to the sum of gamma 1 x1 p1 sat from the modified Raoult's law. Why? Because we know these exist, right? There's a function for the activity coefficient. It's not simply equal to 1, so we have to use modified Raoult's law. Plus gamma 2 x2 p2 sat. But now we don't know what these are. We don't know what the activity coefficients are. So we need to solve for them. And to solve for them, we need to find A. Right, we need to find A here. But we know at the isotrope, right, we know the isotrope will give us the ratio of what? Gamma 1 to gamma 2, right? So let's do some math there to figure that out and try to solve for A. So alpha 1, 2 equals to 1 at the isotrope equals to P1 sat gamma 1 over P2 sat gamma 2. And then we said P2 sat over P1 sat gives us gamma 1 over gamma 2. In this case, at the isotrope, we know what the pressures are. Why? Because these are the data points that are given. P1 sat, P2 sat, at that given temperature. If you didn't know those and you knew Antoine's equation, then you can solve for those using Antoine's equation because you know the temperature in that case. So we do some math. We find that gamma 1 over gamma 2 equals to 331.66 kilopascals over 75.20. The pascals cancel out, and then we get 0.421. Then from the previous problem, we saw how we can get gamma 1 over gamma 2. What do? We subtract the two equations, right? So if I have, this equation minus this equation, then I get natural log gamma 1 over gamma 2. And I know that number, so that will help me solve for A, right? Because x in this case is given, right? X is, in this case, no, actually it's here. So x as at the isotrope is 0.294. All right, so we're going to do natural log gamma 1 minus natural log gamma 2 equals ax2 squared minus ax1 squared. Then we do some math, so we get this, and then we're going to get a x2 squared minus x1 squared. And then we rearrange this. We have a equals to natural log gamma 1 over gamma 2 divided by x2 squared, which is also 1 minus x1 squared, minus x1 squared. So x1 was given as 0.294. So this is given. We plug that in. We know the ratio of gamma 1 to gamma 2, 0.421. We do the math, we get A. So in this case, A is going to equal negative 2.09975. Now we go back to this equation, the bubble pressure. We plug in the values for gamma 1 and gamma 2. We know x1 and x2. We know P1 sat and P2 sat. And then we solve. So then we're going to go back here. We're going to Let me just drag this equation down, I guess. Just go like that. So we have pressure equals exponential negative 2.09975. That's your A, multiplied by x2, which is 1 minus 0.6. Because x1 is 0.6, x2, 1 minus that, squared. So this is your gamma. This here will be your gamma, right? Then you multiply by what? You got gamma multiplied by x1, p1 sat. So x1 would be what? 0.6. P1 sat's given. We just plug that in. So 75.2 kilopascals. And then we add the second part of the equation, which is for the other component. So we got here, again, A, 7.5. Then we have 0.6, which is x1 squared, multiplied by x2, which is 1 minus 0.6. And then multiplied by P2 sat, which is 31.66. You do the math, you find that the pressure is 38.19 kilopascals. So now we have composition in the liquid. We have the pressure. Now we want to find the composition in the vapor. Modified Raoult's law. So then, Y1P equals X1, gamma 1, P1 sat. Y1 is equal to X1, gamma 1, P1 sat over P. Plug in the numbers, you get 0.844. All right? So that answers the question. We found the pressure and the composition in the vapor phase. Any questions? Y2 is 1 minus Y1, yes. Any other questions? All right, so now we're going to move on to the next lecture, so lecture 3.4. And this is where we're going to introduce the K values. So the models we covered were Henry's law, Raoult's law, modified Raoult's law. Now K values are used in a way to look at the ratios of the compositions in a given phase using a table, or not a table, like a chart. Okay? So for given components, we can extract K values and we can use that to solve for the liquid vapor or vapor liquid equilibrium compositions. No, it's not. It's not that. So I'll show it to you now in a second. We're going to define it and then we're going to use it. In addition to that, in this lecture, we also cover flash tanks. So flash tanks is when you have a compressed liquid, then you flash it and you form two phases, liquid and vapor, and it's used to separate based on volatility of the two components. All right, so the K value is a convenient ratio of Y over X, where Y is the composition in the vapor phase and X is the composition in the liquid phase. It's going to be a function of both temperature and pressure. So we're going to look at where we get those in the charts soon. But before we get there, from Raoult's law, the ratio of Y to X is what we see here. So from Raoult's law, if you remember, if we write it down here, we got the partial pressure, YIP equals XI PI sat. So if the ratio YI over XI is K, then I can write this. PI sat over P is equal to K. So that's from Raoult's law. From modified Raoult's law, we have to add the activity coefficient, gamma I. So the same thing. K would be Y over X equals to gamma I PI sat over P. Now we have other ways of writing this. So if we have multiple components, just like we did the bubble pressure and the dew pressure, we had the multiple components, we took the sum and we simplified the equations. The same thing applies here. So if I knew my composition in the liquid phase, then I want to keep the x. So then I take the sum, putting the y on one side, right, and the k on the other side with the x. And in this case, we get the y, the sum of the y's equals 1. So then we get this simplified expression. Then the other way around, if I know my vapor composition, that means I know my y's, I don't know my x's, then I want to eliminate the x in that expression. We take the sum with x by itself on one side, while y on the other side with the k. You do the sum, you get this expression. Why is it useful? Because this will help us solve, right, problems where we know the y values and we don't know the x values. All right. Here we see the K correlation charts. On the top here is the pressure in PSI, absolute. On the bottom we have the temperature. So, and here this is figure 10.13, highlighting that this is lower temperature range. So we have two charts, this one and then this one. This is high temperature range. So here on the bottom, this goes up to 400 Fahrenheit, and the one up here goes only up to 70. Okay, but goes to much lower temperatures. So this is negative 100. Each one of these lines here represents a different material. So this is methane line, this is ethylene, ethane, propylene. So depending on the component you have in your mixture, you would want to find the K values for that given material from this chart. So as an example, let's see this example here. I want to find K values for methane and ethane at 40 psi absolute and negative 60 Fahrenheit. So what do? I'm going to draw a line from the temperature of 60 to the pressure of 40. So this is a straight line from here to here. 40 is given here, negative 60 is given here. Then I go to my material. So methane is the first one. I zoom in on where it intercepts with the line of methane. And I read the value. So what's the value here? 26. Then I go to the line of ethane. And you can see it intercepts there. So here I see the upper, this is ethylene, and this is ethane. So ethane would be right around 1 point. If you say this is 6, 7, 8, 9, 2. So 1.8. So we get that from the chart. For methane, it's 26. For ethane, it's 1.8. Pretty straightforward. So you get those values, then you can use them in problems. All right, so we have an example here for a mixture of 10 moles methane, 20 moles ethane, and 70% propane. Okay, so we have a 3-component system, and the temperature is 50 Fahrenheit. We want to determine what's the dew point pressure, what's the bubble point pressure, and the K values are given by figure 10.13. So the next page here is figure 10.13. Okay, so essentially, so we don't know the pressure, but we know the temperature. In this case, what we're going to have to do, all right, so let me just show you that. So as an initial guess, I think I took 50 here. Okay, so 100 psi and 150. So let's draw that here. So we have 100s here. We have 150 is right here. And the temperature was 50, right? 50, yeah. So that's the point right here. So this is 50. So what do? We draw a straight line. So we go from here. This is going to be, typically you want to use a ruler, okay? This is not the best lines. Okay, they should be straight lines. Then you check where they intercept with the components that you have. So in this case we had methane, ethane, propane. So we got methane here, 6 points, yes. So we got methane, so it's going to be this point and this point. Then we got ethane, this point and this point. Then we got propane, which is going to be this point and this point. That way we can extract the K values. So now I know my, assuming the vapor composition, in this case, we're going to split it into two problems. First one is dew point. Second one is bubble. When I'm trying to find the dew point, I'm assuming my mixture is all vapor. Then I'm condensing. So my assumption is initially that my composition that was given in the problem, right, in the y is 0.1, 0.2, 0.7, right? That was given in the problem. Let me go back and show it. Did I write it on the right side? No, I didn't. So let's see here. So 10, 20, 70, right? That was given in the problem. So that's the initial assumption. At 100 psi from the chart, I found that Ki, 100 psi, right, is 20 for methane, for ethane 3.25, for propane 0.29. Now I calculate what is my composition in the liquid phase. So that condensation, because K is what? The ratio of Yi to Xi. So then if I multiply Ki by, or if I divide Yi by K, I get X. So that's the calculation here. This is my X composition. We check what's the X composition doing that math. We take the sum of all of those and we get this value. Does that make sense? No. Why? It should equal 1. So that means the pressure, the dew pressure, is not 100. Then we try 150. We do the same thing. We do the X calculations. We find that it's 1.174. It's still not 1. In this case, what you could do is linear interpolation. So you take the 100, you take the 150, you take the 1.174 and the 0.8228, and then you find what's the value of P when the sum of X's is 1. So you do that, you find this pressure 126, then you check, what's the K values using the chart, calculate the X's, now it's equal to 1. This is my dew pressure. All right, so we solve for the dew pressure. Then the next thing we want to do is the bubble pressure. In this case, because I want to find the bubble pressure, I'm assuming my mixture is in the liquid phase. And it's just starting to evaporate, just forming a bubble. So I don't know what's the composition in the vapor phase, but I know the composition in my liquid phase. So again, we assume pressures. So in this case, 380 and 400. We calculate what's the value of Y. So Y would be equal to K times Xi. So X would be the one given in the problem. K would be the ones you find from the chart. You do the math. You take the sum, 1.017. This is not it. Check the next one. It's not it. Do some linear interpolation. Find what it is. 385 in this case. Do the math. This is going to be your bubble pressure. All right. So that would be, I think that was all the problem. So yeah, the dew point pressure, we found it, and the bubble point pressure. So that solves this problem. All right, so the next thing is flash separation. So this is what I was telling you about, where we have a tank, and we feed it with a pressurized liquid. Then suddenly we reduce the pressure, and what happens is its temperature will drop, and the two phases will be formed. So if we look at our, for example, our PXY diagram, right, this is PXY, right, X1, Y1, and we draw it like that. High pressure liquid. So where am I on this diagram? Up or down? All right, we're at high pressure, we're somewhere up here. I suddenly flash it, so I try to go for a pressure where I will get two phases with significant amounts, right? Not like one drop of vapor and like all liquid. You want to go to a pressure where you're getting this separation of two large amounts of vapor and gas. So where would that be on this diagram? Somewhere in the middle here, right? Somewhere in here. And in this case, the composition would be what we see here. So the liquid will be this composition, the vapor will be that composition, right? So this is the whole idea of flashing. The important part to note here is right here would be my bubble pressure, and right here would be my dew pressure. So that means the pressure you want to get to is somewhere in between. If you're not in between those, then you don't have two phases. All right, makes sense? So that's basically it. So I guess this is just some words to highlight that. All right. So now we're going to look at the flash calculations. So we're going to have a bit of kind of mass balance in a way, mixed with what we've been looking at in terms of using the K value to look at the ratio between the Y and the X values. So for the flash calculations, we're starting off with a composition, we're going to call it Z. So in this case, Z would represent the liquid phase of my feed. Then we're going to have X, composition of the liquid on the bottom, and then Y of the vapor on the top. So this is ZY because X is already taken here, so we don't want to put X here, essentially. So it's just Z. So Z would be the composition of the feed, then we get some vapor, then we get some liquid. So in a typical problem, we might specify the temperature and pressure in this tank. And we have the composition of the feed. All right? And then we put it in and then we flash it. And we got a balance. So L plus V, so the amount of liquid I have plus the amount of vapor I have in terms of the fraction, right, should equal to 1. This is assuming that the feed is 1 mole. Then we have composition of L plus composition of V should give me Z, which is the composition of the feed. Again, another balance on the amounts that we have. Equilibrium relations, we have Yi equals Ki, Xi. You guys already seen that one. All right, so let's combine those equations to come up with an expression to help us solve a given problem. So in this case, we want to solve these expressions for Z and then take the sum, and then we would basically, we want to take the sum of the Y to eliminate the Y because the Y we don't know. If we were an equation where we had X, we would do the same thing. We would try to eliminate the X and so on. So the way you get this expression is, let me write this down here. So we take this middle equation here. Okay, we got XIL plus YI, V equals Z. In this case, what we have is X equals what? YI divided by K. So this is what you see here. This is where the X was. Then the L here is what? Taking this equation, 1 minus V. So that's what we see here. Okay, and then the rest of it stays the same in that expression, that middle one. Then what we're going to do is just do some math, essentially. So you're going to multiply this into this bracket. Okay, and then you combine to get the V out. And you can try this out at home, I guess. Doing some math, you're going to get this expression. So this will be for one component. So Zi could be Z1, Z2, Z3, it's one component. Then what we do is we take the sum, okay, after rearranging this equation to solve for Y, to make the left side equal to 1. If it's equal to 1, in this expression, we know the K, we know the Z, we don't know what? V. So then we can solve for the amount of vapor we have, and then from that we can find the liquid, and then from that we can find the rest. Okay? So this is the expression where the only unknown is V, and that's what we're going to solve for. Alright, so again, just highlighting solution method, calculate V, then calculate Y for all i's, and then from that we can apply X equals Yi over K to find the x's. Is the pressure that's given between the bubble pressure or the dew pressure. Again, highlighting what I said before. If it's not, then no need for flash calculations. Why? Because you're not even in a two-phase system. If it is, then what we're going to do is use the equation 10.11 to find K. So K would be Pi sat over P at that given, what? Temperature. So if you have a flash, you know the temperature inside, you know the pressure. Pi sat from Antoine's equation will give us the saturation pressures. Then we can solve for K in that given problem using the temperature. Then we're going to substitute the K to the expression that we derived in the previous slide. Right? So now we have the K values. And then by trial and error, solve for V, and then L would be 1 minus V. Okay? So this expression, again, you have a sum of multiple components, and you're trying to find V, so it's not a straightforward expression to solve for. So you'll have to do some iterations to get the value of V. Or if you use a solver, then obviously you can do that as well. Once you've found V, then using this expression, but for a single component, then we can find the mole fractions in the vapor phase, so the Y's. Once I know the Y's, then I can use the ratio of the K to find the X's. Okay? So those are the steps. All right, so I'll do this problem next class, all right, because we don't have time for it. And this is here. This is another problem, 10.6, with its solution. Again, and then this is a home exercise. So I'll do the problem next class and go over it, and then we'll go through the other problem, 10.6. And then for practice, you can try this out, which is a different problem. So you can take this as like a home tutorial in a way for practice, okay? So that is pretty much it for this lecture.